Hello and welcome to chemistry class. My name is Mr. Larkin and I will be your disembodied voice that's going to be helping you go through the notes and learn chemistry. So our first unit is about atomic structure and nuclear reactions. In this unit, we're going to learn about the smallest building blocks of elements, which are called atoms. We'll also look at what happens when the atoms go through nuclear reactions like fission, radiation, and atomic bombs. This unit's broken into 3 chunks, which I'll call standards. I highly recommend that you follow along with this guidance video. The guidance video will provide instructions and review answers. At times, the video will ask you to pause and discuss. I would recommend electing student representatives to be responsible for pausing the video, getting people's attention, calling on random people, and volunteers. Alternatively, the teacher may choose to fill these roles themselves. If you choose to have student representatives, these are my suggestions for expectations. So if you're going to be the person pausing the video, make sure you're sitting near the computer. Pause the video when it says to, and use a timer so that you know when to unpause the video. I might say something like, discuss with your partners for 1.5 minutes. So then after 1.5 minutes, unpause the video. You may also use your best judgment if it seems more or less time is needed for the discussion. If the discussion dies down, or if it seems like it's still really going, then you might want to adjust the timing. If the video is playing and people are talking, pause the video and gently remind people to be respectful. That is, if they're talking while the video is playing, which they shouldn't be. The attention getter is going to be helpful for getting people's attention after after partner time so that we can discuss as a group. So develop a routine. Whatever works for your class is fine. For my class, when I teach it in person, I just have a bell that I ring, and then within 3 to 4 seconds, everyone has to stop talking and get their attention back up front. You could set a timer, or you could do the if you hear me clap once, if you hear me clap twice, if you like that kind of thing. Whatever works for your class, just make sure that it shouldn't take more than a maximum of 5 seconds because you're going to be doing it a lot, because we have a lot of little opportunities to discuss, maybe 5 minutes. And then we're back into whole class playing the video again. And then the people caller is a very important role because even though we'll be doing a lot of partner discussion, it's also important to discuss as a whole class. And to do that in an ordered way, we need someone who can be responsible for saying, okay, who goes next? So after each partner discussion, they're going to facilitate a brief time of whole class discussion. Always start by calling on a couple random people. This helps to make sure that everyone is participating. That should be an expectation in any good classroom. Everyone participates at least a little bit. I would say consider having everyone write their name on cards or maybe popsicle sticks so it's truly random, and then you're just picking a random one out. I don't know is not an acceptable answer because everyone always has an opportunity to discuss first. Something you might want to say is, I'm not sure, but something we talked about was, and then you just say what you talked about. It's okay. It's not a punishment to be called on. It's something that helps a class function well and helps people learn from each other. After calling on random people, take volunteers as time allows, and then, if appropriate, consider taking notes on the board or electing a peer to do so, especially if you're like generating a list of questions or something like that. It helps to have a visual. You could even make this another role if you wanted. Maybe one person's calling on people and facilitating, while another person's kind of taking notes on the board. In any case, whatever you decide to do, whatever works for your classroom is fine, as long as people are learning, because at the end of the day, it's all about the learning. These are the standards that we're going to be learning, that you'll be assessed on over the course of this unit. You'll have a quiz for each of them. A more detailed breakdown of each standard will be provided later in the notes when it's appropriate. So standard 1A says I can explain the most important features of the atom. That's what we're going to start with. Standard 1B is I can model how alpha, beta, and gamma radiation affect the atom and people. And standard 1C is I can explain the process of fission. On our first day, before we really get into those specific standards, we're going to talk very briefly just what is chemistry and why it might be worth to study. So with your partners, I want you to sort the following topics into one of these 4 categories. Option number 1, category number 1, is chemicals. This is any material that is made of atoms. Category number 2 is application of chemistry, something that you do using chemical knowledge. And category number 3 is skills, a learned ability. And then if it doesn't fit into any one of those 3 categories, then you can put it in category 4, things that are not related to chemistry. So if you haven't identified who your people filling those roles are, or if you're going to even do that, then you might want to pause the video now and do that. And once you're done, pause the video, take 5 minutes with your partners, and categorize these topics. Unpause the video when you're ready to go through the answers and discuss as a whole class. Alright, so we're back with Mr. Larkin. We've unpaused the video. Let's take a look. I don't know if I want to go through all of them. I think I'll maybe get through half of them and then you'll notice something. So, potential topics. Cooking. I would say that's an application of chemistry because you use chemical reactions even if you don't realize it when you're cooking. Building is also an application of chemistry, especially if you think about something like cement. Cement is a chemical reaction. There's chemical reactions all over the place. Dating the age of dinosaur bones in the sense of figuring out how old they are, you use radioactive decay, which we'll actually learn about a little bit in this unit. Investigating crime scenes, also an application. Creating medicine is an application of chemistry because you're using, again, chemical reaction. Understanding cell biology is obviously biology, but there's also a lot of chemistry in the cell. Exploring space is an application as well, and so is warfare. Understanding the world could potentially be a skill or an application of chemistry. Refrigeration, also an application. Having fun. Some of you naysayers are going to say it's not related to chemistry. Well, I say hold your breath. It definitely is. I say having fun's a skill. A lot of it's attitude. Bleach is made of chemicals. It has atoms. So is dirt. Dye is also made of chemicals. So is matches. So is polyester. So is cotton. So is steak. Water is H2O. That's 2 hydrogens and an oxygen. Oxygen's made of atoms. Gel nail polish could either be an application or a chemical, depending on how you mean. Pencil lead is actually carbon, by the way, but it's made of atoms. Analyzing data is a skill. You get better at it by doing chemistry, but you analyze data in all sorts of fields, especially nowadays in our modern world. Using models, conducting experiments is a skill, writing's a skill, reading's a skill, arguing with evidence. If you don't have evidence and you're trying to argue in chemistry, go find some evidence, otherwise just listen, stop talking. Using mathematics is useful, so is solving problems, asking questions, communicating, and then coffee's made of chemicals. Which one was chemicals? Number 1. Alright, so pause for a second and discuss with your partners, what was the point of this activity? Go ahead and pause it. This should take maybe 30 seconds to discuss, and then unpause the video. Alright, so I'm not sure what you said, and I'm not sure if my intended point worked, but the goal of this video, or this activity, was that chemistry is everywhere. Whether or not we realize it, it's part of everything we do, and it's all around us. And so why not study it, is the idea. We're going to learn more about our world, and it's going to be interesting. These notes have a lot of readings, so you'll notice instead of lecturing, we'll go through readings. You've got a couple options for how you choose to go through the readings as a class, and I'd recommend maybe taking turns on what you decide to do. So one is that you could pause the video and just give people silent time to read. Introverts really appreciate that, and I think sometimes it's important to do that because everyone is a different type of learner, and it's important for people to be able to learn in the way that's best for them. But at the same time, some people also like kind of reading along, and so I will read them as part of the video. So sometimes you might want to just let the video play and people can read along. Otherwise, you might want to do a little bit of both. You might want to let people read on their own and then do a second read where you'll read along with me. I've even had classes where sometimes people would like to do a partner read, where they kind of take turns reading each paragraph to each other. So in any case, decide what you'd like to do, and then I'm going to go ahead and read this, so if you'd like to read along with me, you can do that. Why study chemistry? The desire to grow and know more about the natural world is a defining characteristic of human nature. Chemistry is a foundational science which grew from humans' curiosity about how stuff works and what it's made of. The study of chemistry is defined as the study of matter and energy and interactions between them. This means that chemistry has many practical and theoretical applications, which is why chemistry is called the central science. Another way to think of chemistry is the study of chemicals and their interactions. So we've got kind of two definitions of chemistry here. Everything's either a chemical or made up of chemicals. Since chemistry is the study of matter, anything made of matter is a chemical. A little definition of what a chemical is there. Water, hairspray, computers, and your pencil are all examples of chemicals, although some are more complex than others. Although the fact that studying chemistry is interesting, connected to the world, should be enough to interest all students, it's important to realize all the useful skills that you gain by studying chemistry. For example, chemists are highly skilled at analyzing data. In our modern age, professionals who are adept at understanding data are highly sought after by companies. Also, chemists must be good at reading, which is what we're doing right now. Being a skilled reader opens doors to professions and other life opportunities that are otherwise closed. Lastly, studying chemistry is a requirement for nearly all science, technology, engineering, and mathematics, that's STEM, degrees. In the Department of Education DOE report from 2014, so a little old, STEM majors earned about $65,000 per year after graduating, about $15,500 more than their non-STEM peers. And there's still a difference. I should look up more up-to-date data because those numbers are larger now than they were 10 years ago. I've got a couple questions for you to work on. Spend a minute on your own first on each question, discuss with each other, and then you can unpause the video and hear what I have to say. So go ahead, pause, work on these two questions on your own first, then together, discuss as a whole class, and then I'll go over answers. Alright, so we're back with Mr. Larkin. We're on the video. What is chemistry? Well, we highlighted two definitions up here, so either one of those is acceptable. So we can say chemistry is the study of matter and energy and the interactions between them. We can also say that chemistry is the study of chemicals and their interactions. Either of those is perfectly acceptable. What are some reasons it may be a good idea to study chemistry? Well, I think there's a lot of reasons, some of which you can pull from the reading, but also, you could make up your own. So one reason that a lot of people like is that it gives access to STEM fields and higher pay. I think another one is that you develop skills like reading, analyzing data, etc. I think it helps you understand the world that we live in. And then again, some of you naysayers are going to be out there saying it's not true, but I think it is fun and interesting to learn about how our world works. Especially at the molecular level, we can't even see what's going on, but we can use it to understand the world. Ah, so interesting. You probably have other ideas as well, and they're probably fine. Let's keep going. All right, so now we're going to go into a story, which is called My Flight Home. It's a fictional story that is set sometime in the near future. Some of the descriptions are graphic and may alarm readers, so that's just a little warning for you. The most disturbing sections are modified from actual survivor accounts from atomic bombs. So the scary sections are real, but it's overall a fictional story. I have some visuals, which I'm going to put on the screen as I read. And so I'm going to move this one away and then resize this a little bit. Okay, there we go. And so if you'd like to read along with me, then don't worry about kind of annotating and trying to understand the text. This is more about an experience, and we're going to come back to this story multiple times throughout the course of the unit to try to understand some of the science that's going on kind of behind the scenes. So like I already said, it's a fictional story set sometime in the near future. Some descriptions are graphic, may alarm readers. The most disturbing sections are modified from actual accounts. Here we go. It had been a fantastic trip. I remember thinking that I wouldn't need to eat ever again after all the bibimbap, barbecue, kimchi, and dumplings. And oh man, the karaoke. You haven't lived until you've belted out Beyonce unashamed to a room full of South Koreans that you hardly know. But the trip was over. I was on my way to the airport on the new maglev train, planning to fly home with a handful of fond memories to look back on. Kim Jong-un had different plans for me, though. At first, I thought it was just a plane. I could see the trail of white clouds following the craft, like so many of the contrails that I had seen before. This one was different, though. It was arcing down toward the city. Perhaps it was some sort of optical illusion, a trick of the eyes. The passenger in front of me saw it too. He pointed and yelled. The cabin turned as one toward the windows, as the white trail clearly took aim at the center of the city. Then there was a moment of blinding light and intense heat. It felt like my eyes and face were on fire. I couldn't see anything. There was a screaming and a smell of overcooked meat. The train lost power and I felt a slight drop. We were no longer levitating. The screeching of metal on metal was deafening. With no wheels to roll on and no power to keep the train floating, the metal coffin was grinding to a halt on the tracks underneath us. My sight began to return just in time to see the shock wave approaching us. It was a wall of gray. I thought that the sound the train made as it slowed was loud. What came next was indescribable. Saying that there was a bang does not do the sound justice. This was the king, the sultan, the czar of bangs to which all other bangs must pay tribute. The windows shattered. The cabin fell over. Rather, it was pushed over. Everything collapsed. There was no train anymore. There was only darkness and weight. There was a weight on top of me, pressing me down into the earth. I knew then that I was going to die. I repeated it to myself. I'm going to die. I'm going to die. I don't know why I bothered to push. There was no doubt in my mind that I was already dead. In the darkness, I saw a sliver of light. I pushed up, and the debris from the train rolled off of me. The sliver of light widened into daylight, except it was very orange daylight. I couldn't see the city anymore. Everything was flat. All I could see was fire. There was a cloud over the fire. It looked like a mushroom, and it glowed from within. It was an evil glow, as if hell itself fueled the upward ascent of the cloud, attacking heaven with unholy fury. The passenger who had been sitting to my left was at my feet, groaning. I helped him up. There was blood all over him. The entire left side of his face was cut open. I could see little shards of glass sticking out, broken pieces of the window we had been looking through. We flipped over some debris looking for other survivors. We called out and received no reply. Eventually we turned from our search and decided to follow the railroad tracks back. There was no clear path anywhere else. I remember passing a river. It was a scene that I would remember for the rest of my life. Although at that point I had already decided my life was over, so I don't know what remembering something for the rest of my life meant. Crowds of people were slowly making their way from the city to the river, all badly burned. I had not realized it before I saw them, but I was burnt too. The flash of light had disintegrated my skin. I touched my face and my fingers came away red. It didn't really hurt, though. I don't know why. Maybe ghosts don't feel pain. Some of the people were naked, their clothes burnt off them. They walked along with their arms raised and something like nylon stockings hanging off them. It was their burnt flesh peeling away. The skin on some people was dark red, obviously burned and painful. No one spoke. It was dreadful. Many of the victims were desperate for water. When they saw the river, they knelt down and drank. Others told them not to. They said, "If you drink that, you'll die." And they did. Every single one. The river was narrow at that point. There was so much floating in it that I thought it might dam the river. I saw corpses. I saw pieces of buildings. I saw a dead horse. There were a line of people following the river. One of them was a mother carrying a baby on her back. The baby was obviously dead. Its head was drooped, its mouth open. Then I saw the reverse. There was a little girl who could not have been more than 3, screaming for her mother, who was just lying there. "Mommy, Mommy!" The woman was bleeding heavily and probably already dead. I knew this was a tragic sight, but my mind was blank. I didn't stop to help her. I couldn't. I don't know how long I walked. Somehow I ended up in a hospital. There were no rooms, but a kind nurse found a mat for me in a hallway. I had already vomited up all of my bibimbap, barbecue, kimchi, and dumplings. Someone said it was because of the radiation, whatever that is. It felt like the flu, but worse. I remember hearing some nurses in the hallway suite talking about the irony of it all. They were part of the radiology department and had regularly used radiation to treat and diagnose people, but now were treating hundreds of people suffering radiation sickness. Their conversation felt unnaturally casual in the context of the suffering around us. "It's terrible what's happening to these people." "Yes, it's tragic." "We deal with radiation every day. Why don't we ever get sick?" "Our doses are smaller. Plus, we use protection, like our lead aprons. If we didn't protect ourselves, we might get sick too." There was a loud booming noise. It was tame compared to the bomb. Only thunder. Nature seemed meek now compared to what I had witnessed. There was rain. It was a heavy rain. It coated the windows of the hospital black. Dust from the bomb carried up into the atmosphere was falling back down with the rain. Fallout, someone called it. They taped off the water fountains soon after and would only let us drink from bottled water. Some days went by, 2 or 4 perhaps. It was difficult to tell. Sometimes a nurse would come and change my bandages. Sometimes no one would come. The hospital started to get more crowded. Apparently people from this town were getting sick as well. Maybe it was just the flu and I had brought it to the town. No, the nurses said it was the fallout. The townspeople drank the black water because they had nothing else to drink. I died 2 days later. I actually died this time. I don't know if the cells of my body just finally gave in to the radiation or if the burns, bruises, vomiting, diarrhea, and dehydration simply took its toll. Regardless, my hallway suite was quickly filled by one of the now sick townspeople. I never did make it home with those fond memories. All right. I want to give you a chance to process a little bit on your own first. So don't jump straight into partners, okay? Go ahead and answer these first two questions. Number one, what emotional reaction do you have to the story? Any and all or none are all fine. So some people have strong emotional reactions, some people have mild ones, some people don't really care one way or the other. But go ahead and spend a minute just kind of thinking about it to yourself and write it down. And then number two, what do you wonder after listening to the story? Go ahead and generate a list. And you should have at least 3 things in your list. As a class, you're going to come up with a lot more than that. But go ahead and generate a list. And this would be a really good time to actually put it on the board as well. So pause, take some time. I would say maybe 1 or 2 minutes for the first question, and then easily 5 or more for the second question, especially once you factor in the whole class discussion. Okay, so you pause the video. We're unpaused. We're back to Mr. Larkin talking on the screen, disembodied voice time. So as far as number 1, there is no right or wrong answer. Personally, I have 2 daughters, so the story about the little kid screaming for her mommy, that always gets me. It's really sad. Like I said earlier, the hardest parts are all true. So this is stuff that has happened and could happen again depending on how countries make their decisions on how they use their weapons. Number 2, what do you wonder after listening to this story? So hopefully you have a list somewhere that you generated. I'm going to put some questions down as well. None of the questions you asked are wrong. There's no wrong answers here. But the questions I'm going to put down are actually things that we might actually hit later on in the unit. So at the end of the unit, you might actually be able to answer some of these things. So one thing at the beginning of the story was the character, the protagonist, we don't know if it was a guy, girl, they, them, whatever, was on a floating train. So what is going on with the floating train? Trains don't usually float. I've never been on a floating train. How's that possible? What was going on there? Another thing was that obviously this bomb wiped out this like whole city or missile or whatever it was. So how can a bomb wipe out a whole city? A building maybe, but a whole city? That's nuts. Something that gets asked a lot is about the black water. Why was the water black? What is fallout? How does that work? And then why did drinking the water end up killing people? We also get asked about the radiation with the nurses and with the sickness. So kind of what effect does radiation have on people / how can radiation be used kind of in a good way? Let's see, what other parts of the story are kind of interesting? Let's see, there's the effect on people. Oh, I guess kind of on the radiation, like, why do some bombs have radiation and others don't? Like a normal bomb won't cause this fallout issue. That doesn't normally happen. All right. Well, there's a few just off the top of my head. You hopefully have a lot more. I know I asked you for 3 at least as an individual. So now that you've kind of discussed and done some questions, I'd like you to spend some time making a model of what happened in the story. So in this unit, we're going to be practicing a lot of modeling. A model in science is a representation of some sort of real-world phenomenon that helps scientists understand how things work, connect, etc. They could be 3-dimensional. That's what a lot of times people think of when they hear the word model, but they don't have to be, and actually none of the ones we're going to do in this unit are going to be 3-dimensional. They can be diagrams, pictures, flowcharts, mathematical equations, computer simulations, etc. So I'd like you to draw a model. So 2-dimensional picture just on the page, explaining as much of what happened in the story as possible. At the end of the unit, you're going to do this again, but you'll be able to include everything that you're going to learn. So try to answer these questions. Take your best guess. we haven't done the lessons yet, so I'm not expecting you to actually know for sure what the answers are or how a train could be floating. But take a guess and try to represent it somehow on your paper. This is going to take a little bit more on your own. So take at least 5 minutes on your own before you even start partnering up. And then go ahead and partner up. Consider stealing your partner's ideas once you do reach that partner stage and refining your drawing based off their ideas. That's helping, not cheating, because we're still learning. If you have a document camera in the room, you could even do some show call. So when your caller person picks some people to share, you could actually put that on the document camera. So go ahead and pause the video. 5 minutes on your own first before you pair up and before you discuss as a whole class. All right, we're back with our disembodied chemistry teacher voice, Mr. Larkin. So I hope that you had some fun drawing those models, and I hope you sparked some curiosity and maybe even have some ideas of how to answer some of those questions that you were brainstorming earlier. Let's get into standard 1A. So there's 3 standards in this unit, and our first one is going to be about the atom. So the standard itself says I can explain the most important features of the atom. As far as when it comes to the quiz, this is kind of the breakdown of what you have to know in order to be able to ace it. So you've got to be able to draw a model of the atom and describe the following pieces: protons, neutrons, electrons, and nucleus. We'll learn about each of those pieces as we go. You also need to identify the charges, so positive, negative, or neutral, and relative masses, heavy or light, of each piece of the atom. You want to be able to describe the relative size of the nucleus. I'll tell you right now, it's really tiny. And you want to be able to use the periodic table to identify the atomic mass, atomic number, number of protons, neutrons, number of electrons, of the most common isotopes of each element. And we'll learn what all that means as we go. So the first thing we're going to do is we're going to investigate something called the electromagnetic force, or EMF for short. So if you have Chromebooks in the room, you're going to need to get those passed out. So you might want to pause the video while you're getting those passed out. And you're going to open up this link, tinyurl.com/onomostatic, and hopefully that works for you. It's going to take you to a simulation where you have a balloon and a sweater. And so you're going to play around with it and try to answer these 2 questions. So number 1 says, how can you manipulate the simulation to create a situation where there is a repulsion, which is pushing away, and attracting, which is pulling towards? And then explain. Include a model, so that means a drawing, as part of your explanation. So when you open this up, can I get it open? Here we go. It looks like this. If you need to Google it, you can look for this link here. Probably just Googling PHET, P-H-E-T, and then balloon static electricity. You'll probably be able to find it pretty quickly. But anyway, this is what it looks like. I would recommend setting it to 2 balloons, and then you can take away the wall and just kind of mess around with this, see what happens, and see if you can get them to attract, see if you can get them to repel, see if you can explain what's going on to make that happen. I would say, as far as timing goes, to answer these, there's 3 questions actually. The last one is just how does it connect to my flight home. Is with your partner, maybe 5-10 minutes, probably more on the order of 10 actually. And then probably check in as a class, see if everyone's good and ready to discuss as a whole class, and then go through it, and I will also go through it after you've had a chance to discuss as a class. So go ahead and pause the video. Let's experiment. Okay, we're back with Mr. Larkin, the disembodied chemistry voice. So number 1, how can you manipulate the simulation to create a situation where there's repulsion, pushing away, and attracting, pulling towards? Explain. So it turns out, if we go to our situation here, if you take those balloons, they pull off the negative charges. And so now, this side of the sweater is positive, and this side of the balloon is negative. And so it'll actually cause the positive and negative to attract each other. Well, I can also do that with this balloon. And so that balloon's also attracted to the sweater. But look what happens when I took the balloons on each other. So this green balloon is actually chasing away the yellow one. Right? The yellow one doesn't want to get too close. So I've got a situation where I have the same charges repel each other, and when they're opposite charges, they attract each other. All right. So let's write that down. So when we have the same charge, they repel each other, negative and negative. When there are opposite charges, they attract each other, positive and negative. As far as your model, I imagine you probably drew something kind of similar to what's going on here. Probably a little simpler, maybe with not as many negatives or positives. I think that's fine. It's a little hard for me to draw on Microsoft Word, which is what I'm using here. So sometimes I will, sometimes I won't. In this case, I'm not going to because you have a visual here that you can kind of model it off of. Number 2, we got some graphing. So now we're doing a mathematical model. When each balloon has a charge, how does the force of the balloons on each other seem to interact with distance? Which of the graphs below best represents the relationship between force and distance? If you didn't get a chance to work on this on your own and discuss with your partner first, go ahead and pause and do that. If you already did, let's keep going. So if I go back to looking at the balloons and the sweater, it looks like it's getting attracted. It looks like it speeds up at the end. So it's going slow, slow, slow. It looks like it's going a little faster. Kind of the same thing if I use the balloons to repel. When they're far away, they don't push as much, right? When I bring them closer, it goes far. If I bring it really close, look how far that was, right? Yeah, so the closer it is, the stronger it seems to get. And so that means that it has to be either A or D. Because here, low distance would mean they're closer. So low distance means a strong force. So it has to be either I or D. A or D, sorry. I don't know that you can really tell from the simulation. We are going to do a reading in a minute. It turns out the answer is D. Right there. There's my attempt to circle with a mouse. But if you put A, I wouldn't feel too bad. I mean, don't feel bad regardless of what you put. But it should be inversely proportional. So when one goes up, when they move farther away from each other, the force should go down. So B and C are both proportional. When distance goes up, so when they're farther away from each other, the force is getting stronger. That wasn't what was happening at all. Oh no, how do I get rid of this? Exit drawing. And then how does the simulation connect to the story we read, My Flight Home? Well, you might have had lots of connections, but one thing that jumps to mind right now is the train. Maybe this was how the train was floating. Maybe they had some charges repelling off of each other or something like that. So let's read about electromagnetic forces. Again, like I said earlier when we were going through the unit, you have different options for what you want to do when you encounter readings. I'm going to go through them one more time. I'm not going to say it every time. So one is that you can read along with me, and I'll do some kind of explanation as well when I do that. Another is that you can just do some silent time and let people read. I think you should do that sometimes for the introverts. You could also even do a partner read where you kind of take turns reading to each other. Or you could do a combination of both of those. In any case, I'm going to go ahead and read this. So if you'd like, follow along with me. Electromagnetic forces. The electromagnetic force is a special force that affects everything in the universe because, like gravity, it has an infinite range, so it never runs out. It has the ability to attract and repel charges, so pull and push. Since material in solid and liquid forms are made of charges having unique order, they too may be manipulated by this force. It is also responsible for giving them strength, shape, and hardness. The electrostatic fields generated among the atoms and molecules near the surface of your hand generate a force field that doesn't allow large objects to pass through your hand. The electrostatic force is also responsible for dirt sticking on your hand. So the dirt is actually attracted to your hand. The electromagnetic force is very strong, and this is surprising too because it can work over an infinite range. To give you an idea, the electromagnetic force is approximately 10 to the 36 power times stronger than the Earth's gravitational field. So to put in perspective, that's 1 and then this many zeros, I'm not even going to try to say that, times stronger than gravity on Earth. Actually, let's try to say it anyway. Alright, so that's 1,000, million, billion, trillion, quadrillion, quintillion, sextillion, heptillion, octillion, noctillion. Ooh, deck? I don't know. Undec? 1 undec million? I'm not sure. I ran out of prefixes. I don't usually go that high. It's a lot stronger than gravity, is the point. Charges create electric fields which drive an electromagnetic force, causing unlike charges to attract, so opposites, positive, negative, and like charges to repel. So when we talk about like charges, that could be 2 positives or it could be 2 negatives. So don't think it has to just be 2 negatives like it was in the simulation. The more charges there are, the more force there will be. You experience the electromagnetic force when you rub a balloon on your hair and your hair clings to the balloon. The balloon absorbs some negative charges from your hair, which leaves your hair positively charged. They are now opposite, and so they attract each other. If you were to make 2 negatively charged balloons, they would repel each other. So it's this diagram right here. The electromagnetic force gets stronger as charged objects get closer together. That's going to be important later. This is why it's easy to keep magnets apart when they are far away, but much harder when the magnets get closer together. As shown in the figure to the left, as the distance between 2 objects increases, the force gets much smaller. On the other hand, if we go to the left on the x-axis, decreasing the distance between particles, the force gets much higher. Keep in mind it's not linear. So distance is more important than how much charge there is, because the charge is actually linear. What would happen if a negative and positive charge were put next to each other and let go? And how does the distance between 2 particles relate to the electromagnetic force? Go ahead and pause the video, take a little bit of time on your own, and then partner up, discuss the whole class, and unpause the video for me to go over the answers of these 2 questions. Should take maybe 1 or 2 minutes each. You can go back into the reading if you need to. Okay, we're back. We paused, we unpaused. What would happen if a negative and positive charge were put next to each other and let go? Because the positive and negative are oppositely charged, they would attract each other and move towards each other. Make sure you have the movement piece as well. Not only would they attract each other, but they're actually going to move because force creates movement. How does the distance between 2 particles relate to electromagnetic force? As distance increases, the force between 2 charged particles decreases dramatically. Wish I had a hotkey for making it red. I want it to kind of stand out a little. Alright, so that was electromagnetic force. Now we're going to move into a different topic, which is called diffusion. We're going to start with another investigation. I want you to observe what happens to the particle of gas when the divider is removed. Start this simulation with 100 blue particles, no red particles, and don't change any other settings. This one has a lot of settings. We're just going to worry about, what did I say, 200? 100 gas particles? So get it set up like this, and then you're going to remove the divider. Before you do, make a hypothesis. What do you think is going to happen? Then I want you to make observations. What do you notice and what do you wonder? And then pick one of these to try to explain what happened. Go ahead and pause the video. Take 5 minutes or so. If you have a little bit of extra time, you might want to also just take an extra 5 minutes to play around with some of these things. And then go ahead and unpause it. And let's see what happens. Alright, so pause the video. Okay, we're back with the disembodied voice of Mr. Larkin teaching us chemistry. So when we remove the divider, we notice these particles are moving around randomly, and since they're moving around randomly, they eventually spread out and they fill the whole container. And so this is kind of a visual way to show what's happening with something called diffusion. If you didn't get a chance to discuss these models already, pause the video. Which one helps you explain similar questions the best? Okay, we're unpaused, we're back. All of these can be used to explain diffusion. This question is really getting into the idea of what makes a model good. And so there are features in all these models that I think are helpful. So for instance, this first model, it has 3 different contrasting phases, and so you're able to kind of compare different situations. it also has some labels and it has some color coding, which you probably don't get to see on yours. This one I like to call a before and after because it has a before and an after. Something I would like is this would labeled if it had like before and after. It has the time, but I would still like more of a labeling. This is also called sequencing because you could have more than 2 stages, right? You could almost have like a comic strip style where you have like 4 different panels or more if something keeps evolving over time. This one also has sequencing. You see it has initial and then later. It also has color coding. What I like about this one as well is it has 2 other features. It has descriptions, and then it also has these zoom-ins. So zoom-ins are useful to show what's happening on the microscopic level in the scene of what's happening on the macroscopic level. So the macroscopic is what you can see with the naked eye, whereas the microscopic, obviously you can't. And then this one also has some labeling, a little bit of color coding, and then it's talking about some vocabulary here with concentration. So that's nice as well. If you had to pick one, I probably would have picked the third one personally. But like I said, this question is really more about what makes a model good. Because over the course of this unit, we want to be drawing good models. So try using some of these techniques as we go through the unit. Try doing some zoom-ins, some descriptions, labeling, sequencing, even color coding if you have markers or pencils. How does this connect to the story we read, My Flight Home? If you need to, pause the video first, think on your own, discuss. Okay, we're back. How does it connect? Well, one way it connects is perhaps this is how the, I don't know what to call it, toxin spread to the other town and made them sick. Maybe it just naturally moved around and spread out like this. All right, we've got another reading. You know your options. Go ahead, pause the video if you need to. Phases of matter. The 3 main states of matter are gases, liquids, and solids. There's actually a lot more than that, by the way, but that's a whole nother class. Google it if you don't believe me. The main difference between each phase, not right now, don't Google it right now, put your phones away. The main difference between each phase is the degree of random molecular motion that occurs. This is a vocab term. Random molecular motion means that there's no set pattern to the way that molecules in a solid, liquid, or gas move. They just move randomly. The molecules in a solid may vibrate, but tend to retain their overall structure until enough heat is added to break the forces holding them together. Liquids have more random molecular motion, but not as much as gases, which have the most. We saw that in the simulation. Those were gas particles in that simulation, and they were just moving all over the place. So here they've kind of used these kind of trails to show the gas is moving faster, is more random. Diffusion refers to the process by which particles intermingle as a result of their kinetic energy of random motion. Kinetic energy is energy related to movement. Consider 2 containers of gas, A and B, separated by a partition, which is just a wall. That's all a partition is. The particles of both gases are in constant motion and make numerous collisions with the partition. If the partition is removed, as in the lower illustration, the gases will mix because of the random velocities of their molecules. So right here in this one, we see them mixing because they took away this wall. In time, a uniform mixture of A and B molecules will be produced in the container. Because each gas is moving randomly, sometimes bumping into other particles and going backwards, diffusion can take a while. The tendency toward diffusion for gases is very strong, even at room temperature, because of the high particle velocities associated with the kinetic energy of the particles. The faster the particles move, the faster they diffuse. Alright, so now we should be able to explain kind of what happened in that simulation that we saw here. It's basically just the gas particles, even though you can't see them, are just naturally spreading around, and so they will spread. That's what they do. Moving into our next section here, we just talked about electromagnetic force, we talked about diffusion, and now we're going to talk about models of the atom. So what I'm going to do for you, I'm going to give an overview, is I'm going to show you 5 different models of the atom. At one point in time, these all were factually correct. What do I mean by that? Well, a scientific fact is what scientists at the time believed through experimentation to be accurate. If new facts come along, they revise that, and they might throw out an old model and replace it with a new one. And that's what we're going to do. So we're going to look at 5 models of the atom, and then we're going to look at some experiments that were done in the last couple centuries, and we're going to go back and we're going to eliminate models that don't work until by the end we have one that works. We know so far already that we need to have charges, because we saw with the balloon simulation that the only way that we were explaining that, and perhaps even the train as well, was by having positive and negative charges. But go ahead and let me read this. Let's just do it all together. The idea of the atom has been around since 400 BC, when Democritus, a Greek philosopher and mathematician, first suggested the idea that matter was made of tiny particles called atoms. Democritus said that atoms were indivisible, indestructible, fundamental units of matter. The word atom is derived from the Greek atomos, which means indivisible. Democritus thought and talked about atoms, but scientific experiments were unknown in his world. Therefore, Democritus did no experiments to test his theories. Over many more centuries, scientists have proposed many different models or ideas about what the atom might be like. More recent scientific advances over the past few centuries have allowed for more scientific experiments and data to be gathered and analyzed about the atom. The pictures below show a variety of proposed atomic models. You will use evidence from historical experimental data to evaluate which atomic model is most accurate based on those experimental findings. So I really want to emphasize this. It's based off the experimental findings. We argue using evidence in this class. So it's not just like, oh, this looks familiar. Oh, I saw this when I watched, a cartoon. So I know that's what the atom looks like because that's how I learn things, is from a cartoon. It has to be based off the evidence. What I'd like you to do is take some time individually and then with your partners and look through each model, annotate it. So make notes on the diagrams. Look through the description, underline important things, write questions down in the margins, and then go ahead and answer these 2 questions. Are there positive and negative charges like in our electrostatic phenomenon? Yes or no? And then where? And can this model be eliminated using experimental evidence? Which experiment? Right now, we only have one experiment, which is the balloons. So you're only going to possibly be able to eliminate things based off whether or not they have charges. But we will keep coming back to this as we go through different experiments. So pause the video and look through each of these, discuss as a class, and then I will go through as well with you. Okay, so we're back. So the plum pudding model, are there positive and negative charges? Yes, there are negative particles and a field of positive. Can it be eliminated? No, not yet. So we're going to leave that blank. Positive center model. Are there charges? Yes. There is a positive center nucleus and negative electrons. So can we eliminate it? No. Nuclear model. This one, yes, also has charges. Looks like protons are positive in the center and electrons are in rings and negative. So can we eliminate it? No. Greek model, as early as 400 BC, blah, 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 indivisible. I don't see any charges. So no, there are no charges. So can we eliminate this one? Yes, we can. Yes, and let's just go ahead and cross it out. Just do an X right there. Cross that sucker out. It does not work. And then it says, using experimental evidence, which experiment? We can use the balloon simulation because we know charges exist. And then charge model, well, this one's in the name, it better have charges. Looks like there's positive and negatives just kind of spread out. Oh no, negative particles are in the center and then positive ones are spread out. So positive spread out and negative in the center. All right, so that means we got 4 models still that we got to figure out which one's right, and we need some more experimental evidence. So the first experiment we're going to look at is the cathode ray, and we're going to start with the simulation again before we go into a reading. So you can open up this simulation, and then I want you to answer these 2 questions. Can you control how the green ray bends? How? And what does that tell you about the ray? And what impact does changing the electrode metal have? What does this tell you? So when you open this up, It looks like this. I think it has a little pop-up. I must have done it already. You turn it on by clicking this button and then this green ray. And then the only things you can change are the display, the electrode, and then you can also change the plates on how negative or positive they are. So like here you see it's really positive, and then here it's really negative, and then here it's neither. So pause the video, go ahead and take some time on your own first, then as partners, then as a whole class, and then I'll go through them. We're back. Can you control how the green ray bends? Yes, we can control the green ray. We could change how much charge was on the horizontal plates. The ray always bent toward the positive charge. So what does that tell you about the ray? Well, if it's always being attracted to positive, that means the ray must be negative. Right? It's repelled by negative, it's attracted to positive, so the ray itself must be negative. What impact does changing the electrode metal have? What does it tell you? It had no impact whatsoever. I couldn't tell. And well, it changed the color. That's all it did, right? But the ray itself didn't change at all. So the ray was unaffected by the electrode metal. So what does this tell you? This tells me that this ray can come from all sorts of metals. So it's not something unique to just one type of metal. Like it's not like you have to have, silver or gold or something like that. So let's read about J.J. Thomson and this cathode ray experiment. This green ray here in the middle might look familiar. It's kind of like our simulation because that's what this guy actually did. And this is over 100 years ago, 1897. J.J. Thomson passed a stream of electric current through many types of atoms in a vacuum tube. When he did this, he observed a glowing ray called a cathode ray come out of each type of atom. The cathode rays passed through thin sheets of foil, so J.J. Thomson knew the cathode rays were made of particles much smaller and lighter than normal atoms. So that's important. So they're not atoms themselves. They're something smaller than an atom. When J.J. Thomson exposed the tiny particles in the cathode rays to positive and negative charge, they were attracted to positive charge, which means they moved toward it, and repelled by negative charge, moved away from it. He reasoned that the small particles were negative since they were attracted to positive charge, and he called these negative particles electrons. So what did J.J. Thomson discover about the atom, and which model of the atom can we eliminate? So what I mean is, from these pages, page 13 and 14, which of these can we now eliminate based off this J.J. Thomson experiment? Pause, discuss, then unpause. Okay, we're unpaused. So what did J.J. Thomson discover about the atom? J.J. Thomson discovered that the atom contains small negative particles called electrons. So which model can we eliminate? So let's go back up here and look at our models. So let's see, we need small negative particles. We've got electrons, electrons, electrons. This one, it says negative particles remain in the center, cannot leave. Well, the electrons obviously can leave because J.J. Thomson was pulling them off. So yes, we can eliminate this. Why? The cathode ray experiment shows that electrons can be removed from the atom. So we've crossed off 2 of them now. Go ahead, cross that sucker off. Doesn't it feel good? Get rid of it. Get out of there. All right, we're down to 3. You might have some ideas of what the next one we're going to eliminate is. But let's see what Ernest Rutherford has to say about this. So this was almost 14 years later. Can you imagine that? Some big discovery about the atom, and then you go for 14 years, you're J.J. Thomson, you think you figured it out, you think you're big man, you think you're the guy, and then here comes someone else learning something new. I imagine Thomson was so interested, right? You think he felt threatened? I don't know. Anyway, in the early 1900s, it was discovered that certain types of rock emitted, which means they shot out, positive particles called alpha particles. These positive particles contain 2 positive charges and have the same mass as a helium atom. Okay, the fact that they're positive is going to be important. Rutherford and his assistant, Hans Geiger, ever heard of a Geiger counter? Prepared an experiment where they fired alpha particles through a small slit about 1 millimeter in diameter. That's really small. At a detection screen shown in Figure 3. They collected the data in Figure 2 below with nothing in the hole as well as thin pieces of gold in the hole. They noticed that the number of particles per minute that hit the detection screen changed depending on the position on the screen as well as how many pieces of gold foil were in the hole. So here was their setup. They had some radioactive source here. This is just firing kind of everywhere. They have a little slit, so it only goes through this part, and then they put little foil there as well. And then here's where they would actually detect whether or not the alpha particles got through or not. So they did 3 different setups. One with no obstruction, so the slit is just empty. One with thin piece of gold foil, and one with 2 thin pieces of gold foil. And so in the middle, kind of makes sense, when they put the foil in, less particles go through. So you can see B and C have much less particles going through than A. What's interesting to me though is, if you look at B, which is the solid dots, and C, which is the open circles, if you move away from the center, there's actually more particles coming through. So the foil is not exactly blocking the particles from coming through. I guess it's blocking them from the center, but it's like spreading them out. Because there's still particles coming through here, a lot more than when there wasn't any foil. That's kind of odd. What's going on there? So we're going to investigate that through, you guessed it, a simulation. So go ahead and follow these instructions and then try to see if you can decide what model fits the evidence from Figure 2 and 3 better. And I'm saying of these 2 models. So this simulation actually has the plum pudding atom and the Rutherford atom as 2 of the models that you can investigate. Those are 2 of our 3 remaining atoms, by the way, our 3 remaining models. So of these 2, which one fits the evidence from Figure 2 and 3? So this idea that when you put gold foil there, particles don't go through in the center, but they kind of spread out. So go ahead and open this up. And you're going to start with, what did I say to start with? The plum pudding model. So you click that. You can turn on the alpha particles by turning on this button. And then you can see them going through. You can turn on the traces if it's hard for you to tell whether or not they're spreading or not. And then if you look down here, you can also look at the Rutherford atom. This has 2 different views. This is zoomed out, this is zoomed in. And you can turn on the alpha particles there as well. So pause the video, experiment with it. Again, 5-10 minutes. It's hard for me to tell, but you can feel it out in the class. And then discuss with your partners, discuss the whole class, which fits the evidence better and why. Pause the video. Okay, we're back. So which fits the evidence better? Well, if you look at the simulation, the Rutherford one is causing the alpha particles to bounce around. Like they're not going straight through. Whereas the plum pudding model, they are going straight through. In the data, in the graph, we see that when the foil's there, the particles bounce around. They get spread out. And so that means the Rutherford model fits the data better because it shows the alpha particles getting spread out. So let's read about that. So Rutherford fired a stream of alpha particles at an extremely thin piece of gold foil as shown in Figure 4. About 99% of the alpha particles went straight through the foil, but 1% were deflected or bounced to the side or backwards. Rutherford reasoned that since most of the alpha particles went straight through the foil, most of the gold foil was empty space. Right? There's nothing in there because it's not slowing them down, it's not hitting them, and they're just going straight through. But what was causing alpha particles to bounce to the sides and backwards? He realized that some of the alpha particles were hitting a dense, so small and heavy, positive center. He called the center the nucleus. It has to be dense because if it's light, they'll just plow through it. Right? It's like shooting a bullet. You know, if you shoot it at paper, it doesn't care. It just goes right through the paper. So it has to be really dense, really heavy. And then it's positive, why? Because the alpha particles are positive, remember? And so the alpha particle is getting repelled by the nucleus, and that's what's causing the bounce. If the center was negative, the alpha particles would just like get attached to it, it'd just attract them. So what did Rutherford discover, and which model atom can we eliminate? So again, go back to pages 13 and 14. We should be able to eliminate another model now. Pause, discuss, unpause when you're ready. Rutherford, what did my boy discover? He discovered that atoms have a small, dense, positive center called the nucleus. He also discovered that the atom is mostly empty space. I mean, really is mostly empty space. Like, if you go to a football stadium, and that's an atom, the nucleus would be the size of an apple. So imagine putting an apple at the center of a football stadium. That's how big the nucleus is inside of an atom. The rest of the stadium, the rest of the atom, empty space, nothing there. Why did I highlight this? It's because I was talking to you at the same time. I want it red. There we go. Should do a different color. Mix it up. All right, so let's see. We got rid of that one. We got rid of that one. We just have these three left. These two have nuclei, which is the polar of nucleus. This one doesn't. So we got to get rid of this one. So we can eliminate this based off of Rutherford's gold foil experiment. The atom needs a nucleus. Okay, so we're down to two. They both have nuclei. They both have electrons. They got positive centers. So let's see, we should have one more experiment, right? Oh, looks like two experiments. Ernest Rutherford comes back on the scene a few years later, and then much later, James Chadwick. What did they figure out? To find out what was in the nucleus, Rutherford fired alpha particles at nitrogen. When he did this, he produced oxygen and heavy positive particles. He called these positive particles protons, and reasoned that they must be in the positive nucleus. Well, that kind of makes sense. The nucleus is positive. You got little positive particles coming off that are still heavy, so maybe that's what's making the nucleus heavy. Chadwick used a metal called polonium to fire alpha particles at beryllium metal. When he did so, the beryllium emitted neutral particles. He called these neutral particles neutrons. In later experiments, he fired alpha particles at many other types of materials, and they all created neutrons. So it's not something just beryllium does. Everything does it. So they all have neutrons. When Chadwick measured the mass of a neutron, he found that it was heavy, so the neutrons must be located inside the small, heavy, dense nucleus of the atom with the protons. So what did Rutherford and Chadwick discover about the atom? And which model can we eliminate? You should have one model left at the end. Aren't you excited? Go ahead, pause, think, write, discuss, and then unpause when you're ready. Oh, you're ready already? Okay, if you say so. So we can say Rutherford and Chadwick discovered that the nucleus contains small, heavy particles called protons. What was that spelling? Protons, which are positive, and neutrons, which are neutral. Neutral means no charge. So which model can we eliminate? Let's go back up. So it has to have protons and neutrons. This one doesn't. So we can say this one can be eliminated based off Rutherford and Chadwick's discovery of the protons and neutrons. So that means we have a winner. All right, you guys want to know a secret? This one's the winner, but it's not the most up-to-date model of the atom. What? I know. You've been lied to. But for our unit, it works. It works for everything, for our unit. And so for this unit, it's what we're going to use, because we don't have any reason to change it. But in the next unit, that might not be the case. Isn't that exciting? You can go home and Google it. Not now. If you want, you can Google most up-to-date model of the atom, and you can learn about it. But for now, let's do this summary of subatomic particles and do a little practice to try to put what we learned into action. So what I'd recommend with this table, take 2 minutes, it's not a long time, see how much of it you can figure out, and then I'm just going to go do it for you. So pause the video, take 2 minutes, see if you can figure this out. Write it in pencil, maybe you'll want to change it. Okay, we're back. So subatomic means inside the atom. There are 3 particles inside the atom that we just learned about, the protons, the neutrons, and the electrons. That's why they're first letters, P for proton, N for neutron, E for electrons. Where are they? Protons and neutrons are both in the nucleus, and then electrons are outside the nucleus. Don't say outside the atom. They're in the atom, they're just not in the nucleus. Protons are positive, specifically +1. Neutrons are neutral, which means no charge, so 0. And electrons are negatively charged, which is -1. Protons and neutrons are both heavy because they're in the nucleus, which contains all the mass, and electrons are light. I'll actually give you the specific masses. 1 AMU, AMU stands for atomic mass unit, and electrons are almost 0 AMU. You see this little squiggle? That's a tilde. Tilde with a T. It stands for approximately. If I actually look it up, I think it's like 0.0009 or something like that AMU. So it does have mass. It's not massless. It does have weight, but it's almost nothing compared to protons and neutrons. So really all the mass of the atom's in the nucleus. If you notice these numbers on the left, you might have been wondering about those. Those actually correspond to the charge and the mass. So the top number is actually the mass, and then the bottom number is the charge. So you can see electrons have basically 0 mass. Again, it's not technically, but compared to neutrons and protons, they do have almost 0, and then they have a -1 charge. Go ahead, pause the video, and spend some time with your partners working on questions 1, 2, 3, and 4. Since there's 4 questions, maybe 2 minutes per question, so you'll probably pause for like 8 minutes or so, and then a little bit of time to go over as a whole class before you play the video again. Okay, you spent a lot of time. You actually did it on your own first, right? You're not just playing the video and getting all the answers immediately, cheating. No, we're not doing that. Number 1, what would most likely happen if a proton and electron were placed next to each other? Protons and electrons have opposite charges and would attract each other and move towards each other. So when I draw, it's really hard because I have a mouse, and then it doesn't stay on the screen if I want to type. So if you really want to admire my amazing drawing here, you're going to have to pause the video. Please don't pause the video. Wow, look at that drawing. Amazing. How are the neutrons affected by the electromagnetic force? Explain. Neutrons are neutral, and so they are not affected by the electromagnetic force. That's actually why they were so hard to discover. They were discovered almost 4 decades after electrons. Can you imagine that? 4 decades? How old are you? Probably not even 2 decades. Definitely not 2 decades. Hopefully you're not 20 years old. Maybe you are. I don't know. Good for you if you are. All right, number 3. If an atom's neutral overall and has 5 protons, how many electrons are there? Explain. So if the atom is neutral, it must have equal positives and negatives. 5 protons would be 5 positives. So there must be 5 electrons to balance out the positive charge. So again, drawing, this is hard. Do 5 pluses. And these are in the nucleus, so I'm going to do like a little circle for the nucleus. And then my electrons are going to be just kind of circling around them. And we've got 5 of those suckers. And so if you think about the entire system, all the pluses and minuses are canceling each other out. Consider a nucleus with 2 electrons. One electron is very close to the nucleus, the other electron is far away from the nucleus. Draw a model, which will be easier to remove. Well, the electron farther away will feel a weaker electromagnetic force and should be easier to take away. This is going to come up later when we start talking about something called electronegativity, which won't be till the next unit. Your model probably looks something like this. You could even maybe do arrows for the force. So that one's going to have a big one. This one's going to have a smaller one because it's not nearly as attractive. Whoa, it's red. What happened? All right, this is a periodic table. You might want to make copies of this so you don't have to keep flipping to this page, because you're going to want to be able to reference the numbers on here. There's a key right here. The top number is something called the atomic number. The bottom number is something called the average atomic mass. And then the symbol, there's 2 letters. The first one is always capitalized, and the second one is lowercase if there's a second one. Sometimes there isn't. And for our class, for the mass, we're just going to round to whole numbers. So like you see 22.9 here, we're just going to call that 23. So we're losing a little bit of accuracy, but this is more about understanding concepts than it is being 100% accurate. We're going to investigate something called atomic mass and atomic number. So everything in the universe is made of small particles called atoms. Everything. If you can touch it, it's made of atoms. However, there are many different types of atoms. Scientists commonly refer to 2 measurements that differ from atom to atom, the atomic number and the atomic mass. Sometimes you'll hear people say atomic weight instead. Tomato, tomato, same thing. Today you'll determine the meaning of these 2 measurements. Number 1. In order to quickly show the atomic number and atomic mass, scientists write isotopic symbols. To the right you can see the isotopic symbol for argon. The atomic number is written on the bottom of the symbol. The atomic weight or atomic mass is rounded and written at the top. Circle and label the atomic mass and atomic number to the right. Go ahead, pause the video for 10 seconds. Follow directions. Circle and label the atomic mass and atomic number. All right, I'm not gonna label them because it's too hard to write with this. But the top one is the mass. Boom. And then the bottom one is the atomic number. If you get those mixed up while you're doing this investigation activity, it's going to be really confusing. So remember, top is mass, bottom is atomic number. Now we don't know what those terms are yet, but we're going to try to figure it out. I want you to practice writing isotopic symbols for the following elements: nickel, oxygen, chromium, carbon, barium, and tungsten. So remember, we're rounding the mass to a whole number, so no decimal, and then we're putting atomic number on the bottom. And when I say bottom, I mean like to the left. So like you're doing like we see here with the argon. So it's to the left, not directly above, not directly on the bottom. To the left, so like top left and bottom left. So go ahead, pause the video and try to do these 6, and then unpause the video. All right, let me do nickel kind of with you. So we're going to put an equation in here. And then make it like that. So nickel, if we find it, is right here. So the atomic number is 28, and then the atomic mass, if we round it, is 59. And the element symbol, if you caught it, was Ni. So 59, and then 28. All right, did I remember that right? Yeah, 28. Oxygen. We love it. We breathe it. It's delicious. Although technically we're not breathing atomic oxygen. We're breathing O2, which is 2 oxygen combined together. So oxygen's right here. Atomic number is 8. Mass is 16. Remember, with isotopic notation, the mass goes on the top. Don't ask me why. I didn't make the rules. It's like, why does a period go at the end of the sentence? I don't know. Let's do one more with you, and then I'll pause the recording and just write the rest of them. So chromium, that sucker's right here. Mass of 52, atomic number of 24. So put a symbol in here. Cr 52. I forgot the atomic number, 24. All right. Bam. All right, so there's the rest of them. Were you mad at tungsten that you couldn't find it? It's a W. Why is it a W? Well, it turns out it's actually from a German word. So a lot of these are from other languages. So these ones all sound pretty similar to the English, but some are from, Latin, Greek, German, like I said. Quietly make observations of the atomic models below. What similarities and differences did you find between the different atoms? Record as many as you can in the table below and on the next page, and then discuss as your group, with your partners, I mean. So a solid circle is a proton, an open circle is a neutron, and then a little dash is an electron. It has the element name on the left, and then on the right it has the overall charge. So there's one here, and then there's 6 others on the next page. So take 5 minutes maybe, and go ahead and write as many similarities and differences as you can. Pause the video. Okay, we're unpaused. There aren't necessarily right or wrong answers. I guess you could say something is similar when it's not, but that's going to be really hard for me to kind of put here. So just generally, without kind of writing it down, they all have protons, neutrons, and electrons. They all have different amounts. Most of them have 0 overall charge. Looks like boron and oxygen don't. Boron is +3. Oxygen is, I think that's a minus. Yeah, it's a -2 right there. They have very similar amounts of protons and neutrons. It's not always the same amount. Like lithium, what's the open circle? Neutron. Lithium has 1 more neutron than it does proton. Looks like boron also has 1 more neutron. Nitrogen, they look even, 7 and 7. Oxygen, they're even, 8 and 8. Fluorine, they're not even. So I guess that's a difference. Sometimes they have even amounts, sometimes they don't. Helium only had 1 circle. These ones all have 2 circles. That's kind of interesting. Anyway, on to number 4. Compare your periodic table with the drawing of boron on the card. Remember, you can look up the atomic number and the atomic mass on boron on the periodic table. With your group, create a hypothesis that tells us what the atomic number represents in the boron atom. So you're only looking at this one right now. You're only looking at boron. All right, write down your hypothesis, and then once you have it, check your hypothesis with every single drawing. It has to always work. If it works with all of them except for one, it's no good. You have to go back and make a new hypothesis. So it has to work with every single atom that is on here. So all 7 of them, it has to work. Otherwise, it's no good. So go ahead, pause the video for a little bit. And then let's see what you come up with. All right, so what did you come up with for your hypothesis? So it looks like the boron has an atomic number of 5. And if I look at there, the only thing that has 5 is the protons. So perhaps the atomic number is just the number of protons. That would be easy. And it works with all of them. So oxygen has 8 protons. There's atomic number of 8. Neon has 10. There's 10. It works with all of them. So what about atomic mass then? So atomic mass, again, let's look with boron first. And create a hypothesis and check it with everything. The atomic mass on the periodic table is decimal. Remember, we're rounding to the nearest whole number. So you might have to round up or down depending on what the nearest whole number is. So go ahead, pause the video for a bit. Investigate. It has to work with every single drawing. All right, did you figure it out? So atomic mass, sometimes people say it's like proton times 2, but that doesn't always work, right? Because lithium has 3 protons, but it has a mass of 7. But if you think about it, the nucleus is where all the mass is. If you count up everything that's in the nucleus, it always adds up to the mass. So lithium has a mass of 7, helium has a mass of 4, boron has a mass of 11. Yep, add it all up, it's 11. That's what's on the periodic table as well. So atomic mass seems to represent the number of, you could say this a number of different ways, right? particles in the nucleus, you could say. Or you could say the number of protons added to neutrons. That's the same thing, isn't it? Because those are the only two things in the nucleus. Something like that. So we're going to do one more, looking at overall charge. What does the overall charge represent? Go ahead, look at boron first. See if you can explain the charges of each of these. Pause the video. Unpause once you think you've figured it out. Alright, this one's a little tricky because there's only two that actually have a charge. It's just boron and oxygen, right? Boron has a charge of +3, oxygen has a charge of -2. Well, if I'm thinking about what I learned in our earlier lesson about the charges in the atom, there's only two things that have a charge, protons and neutrons. I know protons are positive and electrons are negative. So boron has 5 protons and 2 electrons. So that's 5 positives, 2 negatives. If you think about it, those 2 of those cancel out and you're left with 3 positives of the protons. Whereas oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and then it has 8 from the atomic number protons. So that's 2 extra electrons, so it has a -2. Everything else has the same number. 3 and 3, 7 and 7. This one had 2 and 2. So it seems like the overall charge is basically however many protons there are minus however many electrons there are. You could also say maybe the charges of the protons add to the charge of the electrons. But I'll just put it kind of mathematically, is the protons minus electrons. However many protons there are minus how many the electrons there are. Okay. So that works for all of them. So now, it says turn your cards over. Just don't look at that page, I guess. And then using only your periodic table and your hypothesis, I want you to calculate the number of protons, neutrons, and electrons in the chart below, assuming the overall charge is 0. So for example, if I look on the periodic table, helium has an atomic number of 2 and a mass of 4. So now, without looking at the cards, my hypothesis number 1 was that atomic number represented the protons. So then, if the atomic number is 2, that means there's 2 protons. My second hypothesis was that the mass was protons plus neutrons. Well, if the mass is 4 and there's 2 protons, well then how many neutrons there must be? There must be 2, because 2 plus 2 is 4, right? Protons and neutrons have to add up to equal the mass. And then the electron's a little trickier, but it says assuming the overall charge is 0. So then if the overall charge is 0, electrons and protons has to always be the same. So that must also be a 2. Alright, so go ahead, pause the video, and then in, 5 minutes or so, unpause, and I'll complete the table, and we'll see if we're right. Remember, isotopic symbol is mass over atomic number. If you need to, you can pause here, maybe zoom in or something so that you can see all the numbers and check your work. But it should match except for boron and oxygen. So boron and oxygen don't match the cards because this said to assume overall charge is 0, and the cards of boron and oxygen aren't. So that's how you know if you're a cheater. So if you have not 5 electrons for boron and not 5 electrons for oxygen, it means you weren't actually using your hypotheses, you were cheating. Alright, so now you don't need to check them against the cards because you just saw them on the screen. But you should be able to do ones I don't give you cards for. So do these 5. Iron, sodium, argon, lead, and bromine. Again, assume the overall charge is 0. So that means protons and electrons are always going to be the same. And find the atomic number, atomic mass on the periodic table, and then use your hypotheses to find protons, neutrons, and electrons. Go ahead, take some time with your partners, maybe 1 minute each, so 5 minutes, 6, 7 maybe if you have trouble finding them, and complete the chart. Pause as long as you need to check your answers. Hopefully I didn't make any mistakes in my math either. But remember, atomic number is always going to be the same as protons. As long as we assume the overall charge is 0, that's going to be the same as electrons. And then neutrons have to add up to protons to equal the atomic mass. So basically, if you take the mass and subtract the protons, you've got the neutrons. I just summarized how to find the number of protons, neutrons, and electrons, but go ahead with your partners, pause the video, and see if you can write that down. So how do you find protons, how do you find electrons, how do you find neutrons, purely from the product table? Alright, you already tried it first, so how do you find the number of protons? Protons is purely the atomic number, so just look it up. You can find electrons by assuming the overall charge is 0. The electrons will be the same as the protons. And you can find the number of neutrons by subtracting the mass by the protons. Will leave you with neutrons. So there we go. So if you didn't catch that, this reading should cement what atomic number and atomic mass are. Let's read. The atomic number and atomic mass of an element are two defining characteristics for that element. For example, the atomic number and atomic mass of krypton are 36 and 84 respectively. The atomic number is simply the number of protons in an atom of an element. So in this example, krypton has 36 protons in its nucleus because its atomic number is 36. Interestingly, every atom of krypton contains 36 protons. If an atom doesn't have exactly 36 protons, then it can't be krypton. Implied in that is that the electrons and neutrons can change, by the way. We'll get to that later. By definition, atoms have no overall charge, meaning they are neutral. Protons have a +1 charge and electrons have a -1 charge. The only way for there to be no overall charge is for there to be just as many protons as there are electrons. This way, any positive charge from the protons is canceled out by the negative charge from the electrons. So in the case of krypton, there must be 36 electrons as well. There has to be 36 electrons in order to cancel out the positive charge of the protons. It is very hard for an atom to lose protons because they are bound up very tightly in the nucleus of an atom. However, atoms gain or lose electrons quite often. Thus, it is only true that there are as many protons as electrons when an atom is neutral. For this unit, all atoms we're going to work with are going to be neutral. Starting in unit 2 and 3, that won't always be the case. The atomic weight is essentially a measurement of the total number of particles in an atom's nucleus. Since the only two particles in an atom's nucleus are the neutrons and protons, adding them together will give the atomic weight, as shown in the equation below. Mass number equals number of protons plus number of neutrons. We can use this equation and the fact that the number of protons is equal to atomic number to find the number of neutrons for krypton. Remember, the atomic mass of krypton was 84 and the atomic number was 36. So if you just plug it in, 84 equals 36 plus the number of neutrons. If we subtract 36 from both sides, we find the number of neutrons is equal to 48. Summarize how to find the number of protons, neutrons, and electrons from the atomic number and atomic mass. Pause, think, write, discuss, and then unpause. Ah, you've unpaused. Okay. So, protons equals atomic number. Electrons equals protons if the atom is neutral. And then neutrons equals mass minus protons. That is super summarized. There we go. So that is standard A. We're going to move on to standard B. Standard 1B is all about radiation. We're going to model how alpha, beta, and gamma radiation affect the atom and people. We're going to talk about the charge, relative mass, penetrating power, which is basically like how far it can shoot through different materials, and particle identity of alpha, beta, and gamma radiation. Particle identity means like what it actually is. Model alpha, beta, and gamma radiation by writing nuclear equations. Based off a sentence or incomplete nuclear equation, you're going to finish writing a nuclear equation, and then you're also going to discuss the impact that different radiations can have on people. So to start off, we're going to read about two events that happened in history. My recommendation would be to have one person read the top, one person read the bottom, and then just kind of describe them to each other and answer the two questions at the bottom. I will also go through and read it if you'd like to follow along with me Otherwise, you might just want to skip ahead once you've finished discussing to the answers. Henri Becquerel accidentally develops film. Henri Becquerel was a French scientist who specialized in phosphorescence. Phosphorescence is when something glows for a time after absorbing light. Many young, aspiring astronomers place glow-in-the-dark stickers of stars on their ceiling. Stickers that glow in the dark are examples of phosphorescent materials. Inspired by the first ever X-ray of a hand, Becquerel placed some salts of uranium, atomic number 92, so it's a big element, in the window and some photographic plates behind the salts. The photographic plates were covered in black paper so that they would not get developed by the sun. Becquerel hypothesized that when the salts phosphoresced, they may emit X-rays, which would travel through the paper. Well, he didn't get very far into his experiment when it became cloudy in Paris. Therefore, he put the photographic plates in uranium in a desk drawer for a few days. On a hunch, he developed the plates anyway and found that the areas underneath the uranium had been exposed to X-rays. Without any help from the power of the sun, these rocks were able to somehow emit high-energy rays. So they weren't phosphorescing. They were just shooting out X-rays by themselves. Radium girls. In the early 20th century, around the 1920s, a company called United States Radium started to produce watch dials with glowing paint. The paint used radium, atomic number 88, among other things, to achieve the glowing effect. The vast majority of the workers employed to paint the watches and clocks were women. Managers instructed the women to point their brushes by licking them. This allowed the women to paint on the finer parts of the clock, such as the numbers or dashes between numbers. Unfortunately, radium emits high-energy particles, and so when the women ingested it, those high-energy particles killed the cells in their bones. This caused many deaths and health problems, including cancer in some cases. The women sued the companies that they worked for, since the owners and scientists familiar with radium carefully avoided exposure themselves, but let the women do all the handling. Jerks. Alright, you already discussed these, number 1 and 2? If not, pause. So what do you notice about the elements they're doing the emitting in these two examples? Where do they fall on the periodic table? Well, if you find them, atomic number 88, atomic number 92, let's see, 88 is right there, and 92 is right here. These are both the last row. These two rows go in here. You see how these colors match and these colors match? So it goes 57, 58. It's just, it fits on a paper better this way. But this is actually part of row 7. This is part of row 6. So these are both row 7. They're way at the bottom. They're heavy, heavy atoms. The atoms are heavy and fall on the bottom of the periodic table. So maybe there's something to that. Maybe being heavy does something to them. What do you think about the case of the radium girls? Again, there's no right or wrong answer. You can feel what you want. But, I mean, for me, to kind of summarize it, it's messed up. I'm just going to put that. I'm just going to leave it at that. Right? They're abusing just to make a buck, basically, these people. I mean, people died just because they wanted to paint little glow clocks. Not glow in the dark, by the way. Like, these aren't, like, phosphorescent. These, like, glowed by themselves. Really cool, but not worth dying. All right, we're going to do a little investigation here. So for each one of these, do a think, pair, share, pause, unpause. Don't do all three. I think it's better if you do it one at a time. Number 1, what would happen if you place two positive charges next to each other and let go? Pause, discuss the whole class, and then unpause. All right, so if they're both positive charges, they should repel. So like charges repel. So two positive charges should repel and push away from each other. Consider the helium atom to the right. What types of charges are in the nucleus? What would you expect to happen? Remember, the nucleus is just the center. So I'm just asking about the center. What would you expect to happen based off the charges in the nucleus? Pause, discuss, unpause when you're ready. So the charges in the center, there are positive and neutral charges. Neutral isn't affected by electromagnetic force, but the positives should be repelling each other. This is hard for students a lot of times. because you know the nucleus doesn't repel itself. But purely based off what we've learned so far, it should, shouldn't it? Because you got these two pluses right on top of each other. They should be blowing themselves apart. And these negatives aren't helping, because the negatives should also be pulling the positives away. That positive should be pulled toward that negative. That positive should be pulled toward that negative. So this nucleus doesn't make sense. Why is it staying together? Well, let's look at this graph below. What do you know about sections at point 1 and point 3? How might this connect to our understanding of the atom? Pause, think, write, discuss, unpause when you're ready. All right, so it looks like here we have two lines. We have one that says electrostatic force. I'm assuming that's the same thing as electromagnetic force. And then this other one says strong force. So this line is a little loopy. It's repelling here, but then it's attracting here. At point 1, it looks like the electrostatic force is strongly repelling, but the strong force is strongly attracting. And I feel like this one goes down more than this goes up. So that means this is attracting more than this is repelling. Whereas this one, point 3, the strong force is basically done, and the electrostatic force is still repelling. So how might this connect to our understanding of the atom? Well, at the very least, maybe there's another force besides the electromagnetic force, right? What is this strong force? That's the question I think that is kind of odd. Well, and maybe it might help us explain this, though. Because if the nucleus is being held together, something must be holding it together. And it's not the electrostatic force. It's not the electromagnetic force. Same thing. Because the electromagnetic force is repelling plus and plus the whole time. What is this strong force? Well, let's read about it. Let's read about the nuclear strong force. Opposites attract. That is how some people manage to get married, and others miraculously find prom dates. It's also true that like charges repel. These sayings are really referring to the electromagnetic force. When two oppositely charged particles, one negative and one positive, are near each other, they will feel an attractive force pulling them together. On the other hand, when two similarly charged particles, two positives, two negatives, are near each other, they will push away from each other, they will repel. This attractive force between positive and negative is what keeps the negative electrons in the atom. That's what this is showing. Negative electrons are being pulled toward the nucleus. There are positive protons in the nucleus pulling electrons in and not letting electrons escape. So far, everything seems fine. But what if we examine this positive nucleus itself? All the protons and neutrons are in the nucleus. The neutrons have no charge, so they aren't attracted or repelled through the electromagnetic force. They're just neutral. The protons are positive, though, and should repel each other because they have the same charges. Yet we know the nucleus stays together and is very dense because of experiments like Rutherford's gold foil experiment. Right? This dense part, remember, an apple in the center of a football field. So these protons are right on top of each other, and they're not blowing themselves apart. So why is that? The strong nuclear force is another one of the 4 basic forces in nature. The strong nuclear force is stronger than all the other forces, but only when particles are extremely close to one another. In the nucleus, neutrons and protons are close enough together that the strong nuclear force is actually stronger than the electromagnetic force. So it isn't that the protons don't repel each other through the electromagnetic force. Electromagnetic is hard for me to say fast. They do repel each other. It is just that the strong nuclear force overcomes this repulsion. This is only true for stable nuclei. So stable means they're not radioactive. They don't break themselves apart. Some atoms that are very heavy, they have a lot of neutrons and protons, are unstable and emit radiation. Uranium-235 is one such nucleus. It has 92 protons and 143 neutrons. It has so many protons that even the strong nuclear force is not powerful enough to overcome the electromagnetic repulsion between the protons. As a result, the force from the protons repelling each other makes the atom undergo radioactive decay. This is why very heavy atoms are almost always radioactive. They just have too many protons. So that's why the radium girls were getting sick. Radium's really heavy. Its nucleus is not stable. Uranium's also very heavy. It's emitting radiation just sitting there, exposing film. All right, a little practice from the previous standard. Let's make sure you remember still how to use the periodic table to figure out protons, neutrons, electrons. And then questions 2 and 3 are going to be answered based off the reading. So go ahead, think, pair, share each of those, and then I'll go over answers. I completed the chart. Go ahead and pause it if you need to check your answers. Remember, atomic number, protons, and electrons are all going to be the same. Protons because it's based on definition, and then electrons because we assumed the atom's neutral. Neutrons you find by subtracting the mass by the number of protons. Hopefully I did all my subtraction correctly. Of the atoms in question 1, which will be more likely to be radioactive and why? The ones with a lot of protons will be more likely to be radioactive because the protons repel each other strongly enough to overcome the nuclear strong force. So polonium and thorium are radioactive. If you just said thorium, that's fine. But it turns out everything past, bismuth, is always radioactive. Yeah, everything past bismuth. And then stuff below that can still sometimes be radioactive. It just depends on more complicated factors that I'm teaching you. Number 3, what could you conclude about some of the atoms from the fallout from the My Flight Home? Perhaps some of the atoms are radioactive and making people sick. Perhaps. Could be. Could be. Because normal atoms don't make people sick when they breathe them in. Not usually. Let's learn about these different types of decay. Scientists have long been intrigued by the nucleus of the atom. The nucleus seems to defy all logic. Although it is by far the smallest part of the atom, it is also by far the heaviest part of the atom. As scientists continued to study the nucleus, they discovered even more surprises. After Henri Becquerel discovered that uranium emitted radiation, Marie, a pioneering female scientist, and Pierre Curie discovered many other elements that were radioactive. Types of radiation. Naturally, scientists began to wonder what the radiation was made of. To determine what charge radiation had, they exposed the tiny radioactive particles to positive and negative charge. Surprisingly, this test revealed 3 types of radiation: positively charged alpha radiation, negatively charged beta radiation, and neutral gamma radiation. So the alpha one is attracted to negative, so it's going up towards negative. Gamma is not attracted to anything, and then beta is attracted to positive. In alpha radiation, the nucleus emits a helium nucleus, a particle with 2 protons and 2 neutrons. Alpha radiation is easily stopped by tissue paper or skin. However, harm comes if ingested, because then you have nothing to stop it. It's already inside you, so it just rips up your organs. Beta decay occurs when a neutron splits into an electron and a proton. The proton remains in the nucleus, and the electron is ejected at high speed. Beta decay can go through paper, but we stop by a layer of aluminum foil or concrete. Gamma decay doesn't change the identity of the nucleus like alpha and beta decay, and is also the deadliest. Gamma rays are high energy and cause severe radiation poisoning, cancer, and death in those exposed to large amounts. Gamma rays are also used in some medical and food applications to the benefit of humans. It's interesting because they kill cells. So if you want to kill bacteria in food, use gamma. Boom, there you go, kills the cells. Same thing with cancer treatment. Sometimes gamma rays can cause cancer, but if you can direct it, if you can focus them, sometimes they can kill tumors and stuff. So radiation is not always bad. Don't walk away thinking radiation is always bad. This diagram shows as well what stops it. So paper only stops alpha, aluminum stops everything but gamma, and then lead will stop everything. Or like thick layers of concrete can also stop gamma. Isotopes. Even more strangely, scientists found that not all atoms of a given element were radioactive. For example, not every uranium atom is as radioactive. Only certain uranium atoms emit radiation quickly. After many years of extremely careful experiments, multiple scientists discovered that the difference between radioactive and non-radioactive atoms of the same element was the mass of the atom. For example, normal potassium has a mass of 39 AMU, while radioactive potassium has a mass of 40 AMU. These different forms of the same element are called isotopes. In other words, isotopes are atoms of the same element with a different atomic mass. For example, carbon exists in 3 isotopes: carbon-12, carbon-13, and carbon-14. All 3 are carbon because all 3 have an atomic number of 6, and therefore all have 6 protons in the nucleus. However, they differ in the number of neutrons. Carbon-12 has 6 neutrons, carbon-13 has 7, and carbon-14 has 8. This gives each carbon a different mass, even though everything else is identical. And that's what these diagrams are showing. Carbon-12, 13, 14. The only difference is the number of neutrons. Of the 3 isotopes of carbon shown above, only carbon-14 is radioactive. Over time, scientists began to identify many radioactive isotopes, such as potassium-40, uranium-238, and carbon-14, which have been used in technologies ranging from nuclear warfare, bad, to nuclear medicine, good, and radioactive dating of ancient objects, like fossils, interesting. Nuclear decay equations. Nuclear decay equations are often written for alpha, beta, and gamma decay. In nuclear decay equations, like the ones shown to the right, have the parent isotope on the left and the daughter isotope on the right, along with any radiation that is emitted. For example, in the alpha decay example, uranium-235 is the parent isotope. That's this one. Parent isotope right here. And thorium-231, that's this one, is the daughter isotope that is left over when an alpha particle is shot out. So then this would be the alpha particle. 4,2, and then it looks kind of like a fish, the Greek letter alpha. Notice the total mass number and atomic number on both sides of the arrow is always equal. So 235 is equal to 4 plus 231. 92 is equal to 2 plus 90. All right, so then here's beta, here's gamma. What I'd like you to do in this table is to take a little bit of extended time. Do like 2 minutes on your own before you partner up, but then maybe take 5 minutes after that in partners, and complete this table for alpha, beta, and gamma. So go back in the notes. What's the charge of each? What's the mass of each? What's the isotopic symbol? So like how do you write it with the mass and the atomic number? What's the penetrating power? Like what can stop it? And then what effect can it have on humans? That one might be a little hard to find. It's not super obvious in the reading. Some of them have it, some of them don't. But the rest of them should be pretty easy to find. So go ahead, pause the video a little bit on your own first, and then partners, discuss the whole class, and I'll go over it. All right, we're back to the disembodied chemistry teacher, Mr. Larkin. Very good. So alpha is positive, beta is negative, and gamma has no charge, is neutral. As far as the mass goes, alpha is pretty heavy. It has a mass of 4 AMU. Beta is almost 0. It's not actually 0 because it's an electron, remember? Mass of electron. And then gamma actually is 0. So no mass. It's pure energy. It's actually a type of very high energy light. The isotopic symbol, I'm going to do 2 ways. I'm going to do one the way it's in the text, and then I'm going to do another better. I'm going to do another way the way I actually prefer to do it. So let me put these boxes in. So the ones in the text, 4,2, and then it had the Greek letter alpha. Like that. However, it's a helium nucleus. So instead of writing alpha, I just like to write helium, because that's what it is. This is the only one that actually produces an element. Everything else is particles that are shooting out, but they're not actually an element. So like for example, beta, put a beta there, has a -1 charge, almost no mass. Well, what has a -1 charge and almost no mass? An electron. So I just put E for electron. And this is perfectly acceptable. Either one of these is acceptable. Gamma, there's only one way to write it. You have to write a Greek letter gamma, which looks kind of like an alpha taking a dive almost. It's almost like a Y. It has a little loop at the bottom, which isn't really very clear here. Penetrating power. Alpha can be stopped by paper, just about anything, really. Like even if you're like across the room, alpha won't make it through the air to get to you. Beta can be stopped by cardboard, so thick paper basically, or aluminum foil. Gamma, hard to stop, thick lead or really thick concrete. I'm talking like feet of concrete. Effect on humans, harm comes if ingested. I mean, if you get a ton of it on your skin, it can still hurt you, but usually it's really a problem if you eat it. Beta, it didn't talk very much about in the text, but basically like extreme amounts can be harmful, but a little bit doesn't really matter. We get a little bit just walking around the earth. And then gamma, extreme amounts can cause cancer, death, etc. All right, we saw some nuclear equations, but I wanted to do a little bit of just kind of direct examples because people tend to struggle a little bit more with this, but I think once you see some examples, you'll be okay. So nuclear reactions such as radioactive decay or fission, which is standard C, which we haven't quite gotten there, the mass number, which is the top number of the isotope, and atomic number, which is the bottom number of the isotope, are conserved. This means that if you add up the total mass of the reactants, it should equal the total mass of the products. The same is true for the atomic number. So for example, in the reaction above, which is this is a fission reaction, which we haven't gotten to yet, but it's a nuclear equation. It obeys the same rules as radioactive decay does. The reaction above, the total mass number is 236 on the left, because there's only one element there. And the right, since 137 plus 97 plus 2, because there's 2 neutrons, is also 236. So if you want to pause and test that on calculators or do it on paper, if you add it up, 137 plus 97 plus 2, because there's 2 of these, will add up to 236. So you can use that fact that these totals are always equal on both sides to finish incomplete nuclear reactions. So for example, if we knew that uranium-238 was undergoing alpha decay, we would start off by writing the following reaction, since alpha particle is always helium-4. So you start with 238 uranium, which is not a typical uranium atom, right? If you look at uranium on the periodic table, its mass, oh no, it is a typical one, my bad, is 238, but it doesn't have to be. I just want to make that clear. Like this one was 236. The average mass is 238. This is just a slightly underweight uranium atom. It's been on a diet. I don't know. So we have to figure out what's missing. We don't know the unknown particle. But what we do know is whatever the mass is, it has to add up to 238. So the unknown isotope, you can figure it out by basically subtracting the helium mass and atomic number from uranium. So if you do that, you get 234 and 90. And then if you look at the periodic table, atomic number 90 is thorium. The average mass from uranium or for thorium is 232. This one's 234. That just means it's slightly above average. It's fine. Some isotopes are heavier or lighter. So with that little review, and based off the reading with nuclear decay that we did in our lesson, I want you to go ahead and finish these equations, and then write these equations, and then answer these questions. Go ahead and pause it for 10, maybe 15 minutes. Do as much as you can. If you get stuck on number 1, skip to 2, 3, 4, 5, and 6. And then go ahead and unpause the video and we'll go through the answers. So pause please, 15 minutes. Work as much as you can. Extend the time if you need to. And then let's go over the answers. Alright, we're back. I thought about just doing this all while the video was paused, but instead I think maybe doing it together will be more instructive. So here we go. The mass has to add up to be the same, but no mass has been lost, so this is still 234. We lost a -1 because this is beta decay, so we're leaving behind a proton, so the atomic number goes up by 1. And if you look that up, that would be Pa, protactinium. This is another beta decay, so mass stays the same. Atomic number goes up by 1. Here we don't know the parent isotope. It's alpha decay, so we know the parent isotope is bigger, so we just add these back together. 226, and then 88, and that's radium. Remember, first letter is capitalized. Gamma decay does not do anything to the identity of the nucleus. It's still the same atom, it just has less energy. So that's the same isotope as before. The atomic number went up by 1, so that means it lost a negative, it left behind a proton. Mass doesn't change at all, so that would have to be 0. And I'm doing E for electron. You could put in a beta as well, it's perfectly acceptable. Here it looks like we lost 4 mass and we lost 2 atomic number. C4 plus 146 equals 150. So that means this must be helium, atomic number 2. Atomic number 62, we look up on the periodic table. I gotta find it. Samarium. Never heard of it. This one is almost the same as the very first one. The only thing difference is the mass of thorium, but it's still beta decay, so it's the same particle coming out. And notice the mass stays the same, it's just the atomic number goes up by 1. Now this one is interesting. That's a neutron that's getting added to cobalt 59. That makes the mass go up by 1, but 1 plus 59 is 60, so that means this has to be 0. And this would also have to be 0. So that means this is gamma decay coming out. It looks like maybe the neutron had some energy with it, and energy was released as gamma. We've got beta decay here, so mass is unchanged in beta decay. If we add the negative 1 back in, it takes the proton turns back into a neutron, like I'm thinking backwards. So atomic number 27 would be cobalt. Now this one's a little tricky because this is not actually radioactive decay. This one is from standard C, but I just kind of snuck it in there. I thought you might find it interesting. So it looks like the total mass on the left is 236. So here I've got 91, that's 3, so that's 94. So 236 minus 94. Anyone do that in their heads? 236 minus 94. Well, minus 100 is 136. And then add 6 back on is 142. Let's check it. So 94 plus 142. Yeah, it's 236. And then here we got 36 plus 4 is 40. Add 50 more, and then 2 more. So that's 56. And that would be barium. Whew. All right, write an alpha decay of francium-223. So francium, Fr, atomic number of 87. It's on the bottom left of the periodic table. Francium is so radioactive, it exists for like seconds before it blows itself apart. So alpha decay means it's shooting out a helium nucleus. You don't always have to write the alpha decay first, by the way. Addition is commutative, right? 2 plus 3 is the same as 3 plus 2. I just like to do it first. I don't know why. So we're losing 4 mass. So we're at 219 now. And we're losing 2 atomic numbers. So that'd be 85. And if you look at the periodic table, atomic 85 is astatine. We got beta decay now. Potassium 40. Okay, potassium is another one of those that doesn't come from English, so it has K. I think it's Latin this time. Atomic number 19. Potassium's in bananas. So you actually get more radiation from eating a banana than you do from like going to the doctor. Is that true? Maybe bananas over the course of the year. I have to fact check myself actually. Okay, don't quote what I just said. But the point is, sometimes people are scared of like x-rays and things like that because it's radiation. And it is true that a lot of it can make you sick. But radiation is also just a natural part of our life. Alright, so the atomic number goes up by 1 because beta decay leaves behind a proton, so that turns it into calcium. What types of radiation can you identify in the My Flight Home story? Well, we definitely have gamma that burns people's faces off and gives them radiation poisoning. Probably also alpha from people getting sick by ingesting radiation poisoned water, etc. I bet you beta's in there as well. I mean, when an atomic bomb goes off, there's just a mess of radiation. What level of protection would the protagonist have needed? So to protect against gamma, they would have needed thick concrete and lead. So basically, they would have had to be in a military bunker. And hopefully not super close to where the bomb went off, because if the bomb's big enough, it doesn't matter how big the bunker is. What are 2 ways you can determine the type of radioactive decay present in a sample? Well, one way is by measuring the charge. Alpha is positive, beta is negative, and gamma is neutral. Another would be to look at the penetrating power. Alpha is stopped easily. Beta requires cardboard or foil, and gamma requires lead or thick concrete. You could also measure the mass. It's a little hard to do. Alpha is heavy, beta is light, and gamma has no mass. You could also expose animals to it and see what happens, but that's getting a little dark, so I'm not going to write that. Well, let's not do that, alright? Okay, so we're moving on to Standard C. Standard C is our last one. It's a little bit quick. It's continuing talking about nuclear reactions and radiation, but specifically something called nuclear fission. So you need to describe the process of nuclear fission. You need to model fission through both nuclear equations and diagrams, and then use E equals mc squared, you might have heard of that famous equation, to explain the enormous amount of energy released by nuclear fission, and write nuclear equations based off sentences and complete nuclear equations. So let's start off by dropping some bombs on Los Angeles. What? Mr. Larkin, you're insane. Yeah, probably. Okay, so here's a map of Los Angeles. Can you find where you guys are? I live over here. Don't come find me. You guys are creepy. Alright, so we're dropping some bombs on Los Angeles. So I've got 4 bombs that we're dropping. 2 of them are conventional explosives, so that means they're powered by chemical explosions. And 2 of them are nuclear. I have the first nuclear explosion and then the biggest one. So this is probably impossible for you to see, but this is 5 miles. Alright, so the first one, which is a Predator drone, is a blast radius of 50 feet. So that one doesn't even show up on here. 50 feet is nothing. The Moab, which stands for Mother of All Bombs, is the largest non-nuclear U.S. bomb, and that has a blast radius of 0.16 miles, which is enormous for one bomb. Enormous. Right? On the map, it doesn't look like a lot, but I mean that's taken out a whole city block, basically. Like if you look, you can kind of see the blocks, right? So that blows up an entire city block. Boom. Gone. Atomic bombs, though, is just a whole nother category. So the first atomic bomb, one of only 2 that have sadly actually been dropped on people, was called Little Boy. The other was Fat Man. If you're interested, you can Google it yourself. Not now. Put your phone away. So that had a blast radius of 2.8 miles. So from one end to the other, almost 6 miles of damage. So that's basically all of downtown Los Angeles. And then the biggest one, which was from the USSR, was the Tsar Bomba. And that has a blast radius of 57 miles. So basically from Santa Monica all the way to Covina, Riverside, Fontana area. Insane. So what do you notice? What do you wonder after reviewing that data? How do conventional bombs compare to nuclear bombs, and why do you think there is such a large difference? Go ahead and pause the video. Think, write, discuss. On pause when you're ready. So I think the biggest difference is that the nuclear bombs are tremendously more destructive. Like, insanely more destructive. So why do you think there's such a large difference? I'm just going to put question marks right now. That's what we're going to investigate. Anything you said, interesting. I'm glad you volunteered it. Interesting to discussion. Why do you think there's such a large difference? I mean, this is not just like, oh, it's a bigger bomb. Like, if you look at the actual size of the bombs, they're not that much bigger. Well, they're bigger than the Predator drone. But the Moab is about the same size as Little Boy. But the Moab, I mean, that's a whole city block. But it's nothing. That's a whole city. Not Los Angeles, but downtown. That's a whole city. That's insane. So here's what we're going to do. I'm going to have you compare a chemical reaction, which is this combustion of methane. Methane is natural gas, so if you have a gas stove, this is the reaction you're doing. This is a chemical reaction. You might want to write that there, chemical. To fission of uranium-235. This is a nuclear reaction. You might want to write that, nuclear. I have a reaction equation. I have the masses of the parts of the reaction, and have the energy released, and this is in kilojoules per gram. Kj is kilojoules. That's a unit of energy per gram, so per mass of reaction. There's some terms I'd like you to use while you're eventually discussing. Start on your own. Atom, that's the basic unit of an element. So for example, O2 is 2 oxygen atoms. A compound or molecule is a combination of multiple atoms. So for example, O2, which is this one right here, that's 2 oxygen atoms bonded together. Unit 3 will talk about bonding. Reactants are the chemicals that begin a reaction on the left of the arrow. So for example, these two are the reactants. And then products are the ones on the right. So that would be these ones. P for products, R for reactants. I think I switched to a highlighter accidentally. Oh well. So go ahead, take some time on your own first. What similarities and differences do you notice between each type of reaction, and what is changing in a chemical reaction, what is changing in a nuclear reaction? Again, the one on the left is chemical, the one on the right is nuclear. Go ahead, pause the video. Unpause when you're ready. Okay, so we've discussed. I'm going to put some things for number 1. I might not capture everything that you identified, because honestly, there's a lot of information here, right? But some similarities I notice is they both have changes. They both released energy. What else? They have atoms. They have masses. Those are all similarities. What are some differences? The nuclear equation has bigger masses and much more energy. Insanely more energy. The nuclear equation has the masses and atomic numbers in. No compounds in the nuclear equation. It's just atoms. Did you catch that? Like, this is just uranium. It's not connected to any other atoms. Let's see, what else? What else? Oh, you know what? If you look carefully at the chemical one, it's carbon, hydrogen, oxygen, and at the end it's carbon, oxygen, hydrogen, oxygen. The same atoms, they're just rearranged. So chemical one only has carbon, hydrogen, and oxygen atoms. Whereas this one, the uranium actually turns into 2 different atoms, which is actually what the difference is. So in a chemical reaction, the compounds change, but the atoms don't. In a nuclear reaction, the atoms turn into new atoms. I need to get this back on this page somehow. All right, there we go. All right, for number 3 and 4. Number 3, you're going to compare how the total mass changes from reactants to products for the chemical and nuclear reaction. before you look at number 4, I want you to make a prediction. Do you expect the mass to go up, down, or stay the same for each type of reaction? So think, write, discuss, and then discuss as a whole class. Unpause when you're ready. Number 3 is a hypothesis. There's no right or wrong answer, so I'm not going to write anything here. But we're ready for number 4 now. So I want you to compare the total mass of reactant products for both reactions. Remember, reactants is the beginning and products is the end. I've actually shown my work here. I've done the calculations for you, but you're really just looking at the totals. So this is the total this is the total reactants, this is the total product. Total reactants for nuclear, total products for nuclear. What do you notice? Go ahead. Pause the video, think, write, discuss, report, unpause. Okay, we're unpaused. So if you noticed, the chemical reaction doesn't lose any mass between reactants and products. The nuclear reaction loses a tiny bit. Like, let's calculate it. 236.05. You know, I don't want to. Those numbers are too messy. But it's like 0.1. Like, it's less than an AMU. Right? It's a very small amount. So make a hypothesis. Where do you think the mass is going? What you notice from question 3. That should be question 4. Where is the mass going? Go ahead. Pause the video. Think, write, discuss, report. Alright, you're back. Oh, you think I'm going to tell you? Ah! No! Ha! It's a hypothesis. I'm not going to tell you. Nah, I am. We're going to read it right now. Fission! When the nuclei of certain isotopes are bombarded with neutrons, they undergo fission, the splitting of a nucleus into smaller fragments. Uranium-235 and plutonium-239 are fissionable materials, as shown in Figure 1. Plutonium is not in here. Well, this is just uranium. But anyway, as shown in Figure 1, a fissionable atom, such as uranium-235, breaks into 2 new atoms of roughly the same size when struck by a slow-moving neutron. So you see we've gone from the uranium to 2 atoms here, the krypton and the barium. At the same time, more neutrons are released by the fission. These neutrons strike the nuclei of other uranium-235 atoms, continuing the fission by a chain reaction. In a chain reaction, some of the neutrons produced react with other fissionable atoms, producing more neutrons, which react with still more fissionable atoms. This process is similar to the toppling of dominoes shown in Figure 2. So you knock one down, produces more neutrons, knocks others down, produces more neutrons, and then it just keeps going and going and going. The splitting of an atom releases an enormous amount of energy. I really can't stress this enough. It is mind-boggling how much energy splitting an atom releases. Chemical reactions cannot even come close to the amount of energy released in nuclear reactions. The reason is that a tiny amount of mass is actually converted to energy in nuclear reactions. Did any of you guess that? I'd be impressed. I wouldn't have guessed that. The energy produced is given by Albert Einstein's famous equation E equals mc squared, where E is energy, m is the mass lost, and c is the speed of light. Well, it turns out the speed of light is very large. 300 million meters per second, or 670 million miles per hour. Therefore, even a very small amount of mass will result in a relatively large amount of energy. This is why nuclear bombs are so powerful and why nuclear power plants can make energy from so little fuel. So basically, some mass turns into energy, and the amount of mass lost can be tiny, but then you multiply it by the speed of light squared, and you'll still get a bunch of energy. It's not disappearing at the speed of light. I mean, it's fast, but it's not that fast. But it's being multiplied by the speed of light in the equation. So the point is the product, which is what the number is called when you multiply things, is a really big number. Fission reactions use nuclear reaction equations just like radioactive decay does. In each fission equation, the total mass number and atomic number of the reactant products are equal. Even though mass is technically lost in all fission products, fission processes, the amount lost is so small that since the mass numbers are integers, it doesn't show up in the written nuclear equation. The reaction below is the same fission reaction from Figure 1, but written in the customary format. So this is the same reaction, but now they've used the isotopic notation, mass number on top, atomic number on bottom. The 10N is neutrons, and then the 3 in front just means there's 3 neutrons, which is what you see if you look here. 1, 2, 3. So let's do some practice. I would recommend doing, think, pair, shares for each question. So break it into chunks rather than just giving like 15 minutes to do the whole thing. Just give a few minutes for one, pause, unpause, etc. I'm not going to say pause, unpause each time because I'm getting a little tired of it. Are you? Oh, you don't like the disembodied voice of Mr. Larkin? That's hurtful. I'm crying over here. Number 1. How can you use E equals MC squared to explain the map data from page 1.38 when we drew circles on the map? This page number is wrong, isn't it? So this one. 139. Ah, I was so close. Forgot to edit it. Alright, so we can use E equals MC squared to explain why the nuclear bombs were so powerful. Bombs were so powerful because in nuclear reactions, a little bit of mass is converted to energy according to E equals MC squared. The mass lost is multiplied by a huge number, speed of light squared. And so even a little mass releases tons of energy, enough to blow up a city. I should be clear, it's not one atom that gets split. They're splitting a bunch of atoms, but it still releases a lot more energy than chemical would. Alright. Pause, think, pair, share. Complete the nuclear reactions below and determine if they are fission reactions or not. Oh, I can't edit this first one. Oh no. Alright, well, I'll draw it, but it's not going to stay. Alright, so 92 plus 0 is 92. That has no atomic number, so what do I have to add to 55 to get to 92? Adding 5 gives me 60, 30 more gives me 90, 2 more, so this would be 37. Oh, you know what, I'm dumb. I could have just looked it up on the periodic table, because it's rubidium. It's always going to have the same atomic number. Durr. And then here we've got 236 atomic mass on the left. And then 137 plus 95. Let's see. That'd be 237. Take 5 away. Would be 232. So then we need 4 neutrons, because they each have 1 to get up to 236. Did that right? Yeah, I did that right. Okay, how about these other ones? Well, this is... Oh, so was that fission? Yes, it's fission because it creates 2 new elements. Is this one fission? No, because xenon's an element, but an electron is not. This is beta decay. This one is beta absorption. So you got one element turning into one element. It's just absorbing an electron. So a proton and electron are combining and turning into a neutron. This one, I don't know how to classify it, because you're combining atoms, but then they're breaking up. So I would actually say there's an intermediate step that's not shown, but the second half is fission, because you're splitting into 2 new elements. And then this one I can already tell is definitely fission, because we start with uranium, but we end with barium and krypton, so that's 2 new elements. Alright, so barium has atomic number 56. We got 3 of these, that's 96 plus 140. So that's 236, but one of them has to be the neutron, so 235 for the uranium. If plutonium-244 breaks into 2 neutrons, strontium-90 an unknown element, write the nuclear equation for this process. No problem, I'd love to. So we start with the mass. Plutonium-244, plutonium's Pu is stinky plutonium. Atomic number 94, it's just 2 past uranium. And then it's going to break into 2 neutrons, so I'll do that first. I'll just go in the order it gives me. So 2 and 10N, and strontium-90, so that's a mass of 90. Let's find strontium. Where's strontium? Come here, strontium. Atomic number 38. There you go. Alright. and then an unknown element. Okay, so we got to figure out what the unknown element is. So let's do atomic number first. So what do I have to add to 38 to get to 94? I add 2 to get to 40, and then 50 more, and then 4 more. So that's 56, right? So that would be barium. This guy's popping up a lot for some reason. And then I've got 92. What do I have to add to 92 to get to 244? 92. Well, I add 2 to get to 94, and then 154. That's not right, is it? That's too big. That's a very large mass for barium. Okay, 92, 154. No, it's just, that's going to be a very unstable barium. Because the average atomic mass for barium, right, is 137. So that barium's going to last less than a second, promise you. But fission is a chaotic process, so that's definitely still possible. All right, plutonium-240. We got plutonium again, but this one is a little lighter. It's just a different isotope. They don't all have to be average. Produces xenon-134. Oh, you know what? I had xenon up here, right? Atomic number 54. Ah, don't even need my periodic table. And one other isotope with no neutrons. Oh, that makes it a little easier. So this would have to be 40. Atomic number 40. Come here, come here. Zirconium. And then 134, 106. Also a very heavy zirconium. Write a nuclear equation for the fission reaction that starts with uranium-235 and produces 3 neutrons, barium-144, and krypton ? No problem. Love to. Let's do it right now. 35, uranium, 92. It doesn't say it's hit by a neutron, so I'm not going to put a neutron in. I know a lot of times there is a neutron coming in to kind of start the fission, but there doesn't have to be. All right. 3 neutrons coming out, though. So there's our 3 neutrons. And then we got barium-144. That's Ba. Barium with a bad attitude. Anyone ever say that to you? Hey, you have a BA. Stands for bad attitude. If you're still saying chemistry is not fun, you have a BA. Yeah. Alright, remember I can't just use the mass from the periodic table. I have to calculate it. So we got 3 plus 144 is 147. And what is that to 235? So 147 plus 3 is 150. And then 53 gets me to 200. Plus 35 more, so 53 plus 35 is 88. Write a nuclear equation for the fission reaction that starts with unknown isotope and produces lanthanum-148, bromine-85, and 3 neutrons. Okay, but only because you asked nicely. Last time. Alright, so I'm leaving the first one blank while we write these other ones. Because all we're going to have to do is basically add everything on the right up to figure out what's on the left. But it's easier to write it out first. Lanthanum. Atomic number 57. It's like a little scavenger hunt to find these. You're going, Mr. Larkin, how do you find them so fast? Well, teach chemistry for a decade. You'll probably find them pretty quick. Honestly, you should be saying, why is it taking you so long? Also, why are you writing 0 for a neutron? That's silly. Okay, let's add all these guys up. So I'm going to take 2 of my neutrons. That's 150. 150 plus 85 gives me 235. Plus 1 more gives me 236. Is this going to be uranium again? I bet it is. 57 plus 35. I'm going to take 3 away there, make that 60. That's 92. It's our old friend. Hello, uranium. Alright, that is it for Standard 1C. This next part is a review of the entire unit. So we've reached the end of the unit. We've learned a lot. We're going to go back to our models of the My Flight Home story. You remember that story all the way back on pages 4, 5, and 6? Work with your partners to include all the content in the table below. If you have big sheets of poster paper or butcher paper, use that because it's not going to fit on a normal piece of paper. We have learned too much. Otherwise, tape 4 pieces of paper together to make a larger one. Spend a few minutes brainstorming story connections as a class before you get started. Your visual models need to show and explain, so you need to use your modeling techniques like zoom in, sequencing, color coding. You need to have labels and descriptions. You need to cite page numbers. Anytime you're putting information, put where you learned it from. Because I want you to be using the notes as you're doing this, so that will force you to use the notes. The story and content pieces should be connected to each other. You should not be doing 5 separate models. It should be all flowing together. So think about how you can use sequencing, zoom-ins, etc. to show how things fit together. So here's the content that we've learned. Electromagnetic forces, diffusion, structure of the atom, radioactive decay, and nuclear fission. I'm such a nice guy. I put the page numbers where you could find the readings for each of this content. And I want you to take some time as a class to decide how it connects to the story. I'm not going to write this part for you. Go ahead and do a think, pair, share, discuss as a class. Where does electromagnetic forces fit into the story? Where does diffusion fit into the story? How could you fit the structure of the atom in? Well, that one could fit in anywhere actually because atoms are everywhere. I gave you one anyway. Too nice. Radioactive decay, where's that fit in? Where's nuclear fission fit in? By the time you're done, and this is going to take you 30 minutes at least, you should have a poster that shows and explains everything we learned this unit. I hope you had fun this unit. I'm looking forward to the next one. It's going to be amazing. We're going to talk about space and the sun and the Big Bang. It's going to be so cool.